Simplex method for solving linear programming problems with less than or equal to constraints. In the previous lessons, we used geometric method, that is graphic method, to solve linear programming problems. But the graphic approach will not work for problems that have more than two variables. For problems with more than two variables, the recommended algebraic method that is efficient enough to solve them is simplex method. Simplex method is an efficient standard technique in linear programming problem for solving and optimization problems, typically one involving a function and several constraints. It's efficient because it doesn't compute the value of the objective function at every point. Instead, it begins with a corner point of the feasible region where all main variables are 0 and then systematically move from one corner point to another point while improving the objective function at each stage. This process continues until the optimal solution is reached. For better demonstration of simplex method, let's start with this simple example having two decision variables. The example is this. Mr. X holds two part-time jobs, job A and job B. He never wants to work more than a total of 18 hours a week. He has determined that for every hours he works at job A, he needs 2 hours of preparation time, and for every hour he works at job B, he needs 1 hour of preparation time, and he can't spend more than 24 hours for preparation. If he makes 400 per an hour at job A and 300 per an hour at job B, how many hours should he work per week at each job to maximize his income? Simplex method is a 7-step method with a possibility of repeating step 4 to step 7 twice or more. Just like graphic method, simplex method starts with the formulation of mathematical model. So let's start with the formulation of mathematical model. Step 1, formulate mathematical model. Let x1 is equal to the number of hours per week Mr. A will work at job A, and x2 is equal to the number of hours per week Mr. X will work at B. Thus the mathematical model is z max is equal to 400 x1 plus 300 x2. This is the objective function, which is subject to x1 plus x2 less than or equal to 18. This is weekly working hours. To x1 plus x2 less than or equal to 24. This is weekly preparation hours. x1 greater than or equal to 0 and x2 greater than or equal to 0. This is a non-negativity restrictions. Step 2, convert the inequalities into equations or add slack variable for each constraint to obtain a standard form. Why addition of slack? As we know, slack is any capacity, input material or time left unused by the left-hand side expression. Hence, the expression on the left-hand side is always less than or equal to the expression on the right-hand side. To make these two sides equal, that unused capacity, input or time must be added to the left-hand side. Slack will not only be added to the constraint, but also to the objective function. But their coefficient on the objective function is 0, because they don't have any contribution for maximization of the objective function. Adding the slack variable to each of the constraint and objective function permit us to write the mathematical model in standard form as z max is equal to 400 x1 plus 300 x2, which is subject to x1 plus x2 plus 1s1 is equal to 18. This is weekly working hour. 1s1 is the slack associated with less than or equal to constraint in equation 1, but its coefficient is 1. 2x1 plus x2 plus 1s2 is equal to 24. This is the weekly preparation hour. S2, that is the second slack, is associated with the less than or equal to constraint in the second equation. These slacks, that's S1 and S2, should be added to the objective function, but their coefficient in the objective function is 0, since they don't have any contribution for maximization of the objective function. So, the objective function is modified to z max is equal to 400 x1 plus 300 x2 plus 0 s1 plus 0 s2. The formulated mathematical model contains two simultaneous linear equations with 4 variables. Whenever a system of simultaneous linear equations have more variables than equation, we can expect an infinite number of solutions. how we can expect an infinite number of solutions. Let us see some of the solutions. Just by assigning 0 to any two variables, we can compute the values for the remaining two variables. If x1 is equal to 0 and then x2 is equal to 0, then s1 is equal to 18 and s2 is equal to 24. Just substitute. If x1 is equal to 0 and x2 is equal to 0 in the first equation, then s1 is equal to 18. Again, substitute. If x1 is equal to 0 and x2 is equal to 0 in the second equation, then we will get s2 is equal to 24. Similarly, if x1 is equal to s1 is equal to 0, then x2 is equal to 18 and s2 is equal to 24. If x1 is equal to s2 is equal to 0, then x2 is equal to 24 and s1 is equal to 18. If x2 is equal to s1 is equal to 0, then s1 is equal to 18 and s2 is equal to 24. If x2 is equal to s2 is equal to 0, x1 is equal to 24 and s1 is equal to 18. If s1 is equal to s2 is equal to 0, then x1 is equal to 6 and x2 is equal to 12, meaning we find 6 solution by assigning 0 to any of the two variables. The same scenario is true for a number other than 0. Therefore, whenever the number of variables are more than the number of equations, the number of solutions are infinite. The simplex method can be viewed as an algebraic procedure for finding the best solution to such a system of equations. When we say the best solution, it is a solution that satisfies the following two requirements. 1. It maximizes or minimizes the objective function. 2. It satisfies the non-negativity requirement. This second requirement demands that the value at the right-hand side of the equation have to be positive. In our constraint equations, both values to the right-hand side are positive. The 6 solutions we determined by assigning 0 to any two of the 4 variables are called basic solutions. For any standard model having n number of variables and m number of equations, the basic solution is determined by setting 0 to n minus 1 number of variables. In our particular case, the number of variables are 4, that is x1, x2, s1 and s2, and the number of equations are 2, that is equations of working time and equations of preparation time. And we set 0 to 2 of the variables, that's 4 minus 2 is equal to 2, to determine the basic solutions. Basic solution is feasible only if all the variables are positive, that is if it fulfills the non-negativity requirement, otherwise it is infeasible. In our part-time problem, the variables in all 6 solutions are positive, hence all the solutions are feasible solutions. But in solving problems, it is the decision variables that should be set to 0, but not the slack, as we did in solution 1 above. The variables, when their values are set to 0, are called non-basic variables, and the remaining variables, that is the variables of which the value is calculated after setting 0 to the non-basic variable, are called basic variables. For example, in our basic solution 1, x1 and x2 are non-basic variables because we set 0 to them, and s1 and s2 are basic variables because their values are determined by setting 0 to s1 and s2. Step 3. Set up the initial simplex tableau. To construct the initial simplex tableau, simply set the decision variable equal to 0, meaning set the decision variable as non-basic variables, and solve for the values of the slack variable, meaning the slack variable becomes basic variable. For our part-time problem, s1 is equal to x2 is equal to 0, and then s1 is equal to 18 and s2 is equal to 24. After determining the non-basic and basic variable, let's draw a table with n plus 2 columns and m plus 2 rows, where n is the number of variables and the 2 columns added are 1 for basic variable, 1 for values of basic variable. On the other hand, m is the number of equations and the 2 rows added are 1 for variables of the objective function and 1 for coefficients of variables in the objective function. So the initial tableau can be set as like this. This tableau contains 6 columns and 4 rows. 6 columns, 4 variable plus 2, and the 4 rows are two equations plus 2. The variables, values and coefficients can be filled as follows. First, write the variables of the objective function and their coefficient in the first two rows. Write the variables in the first row from second to fifth column and their coefficient in the second row as the corresponding column. That is, the variables are x1, x2, s1 and s3. 400, the coefficient of x1 in the objective function is below x1. 300, the value of the coefficient of x2 in the objective function is below x2. 0, the coefficient of s1 in the objective function is below s1. And 0, again, the coefficient of s2 in the objective function below s2. Write the basic variables at the left-hand side column and their value at the right-hand side column. Basic variables are set under bases at the left-hand side column. In our case, the bases are s1 and s2. Thus, we set s1 at the third row and s2 as the fourth row. 18, the value of s1 is set at the corresponding right-hand side column, and 24 to the right-hand side column of the fourth row corresponding to s2. Third, write the coefficient of each variable in the column associated with that variable. 1 is the coefficient of x1 in the first equation, is set at third row under x1. 1 again, the coefficient of x2 in the first equation is set at the third row under x2. 1 again, the third one, the coefficient of s1 in first equation is set under s1 at the third row. We don't have s2 in the first equation. In such case, we will write 0 under that variable. Again, we will write 2, the coefficient of x1 in second equation, under x1 at the fourth row. 1, the coefficient of x2 in the second equation will be written at the fourth row under x2. We don't have s1 in second equation, so we will write 0 under s1 at fourth row. 1, the coefficient of s2 in second equation will be written at the fourth row under the column s2. To move from an initial basic solution to a better basic feasible solution, the simplex method must generate a new basic solution that yields a better value for the objective function. To do so, it requires changing the set of basic variables. To select one of the current non-basic variable to be made basic and one of the current basic variable to be made non-basic. For computational conveniency, we will add one new column next to the left-hand side column, that is here, and we will list the corresponding objective value coefficients for each of the basic variables. Also, to find whether it is possible to move from one basic feasible solution to another, we will add 2 new rows to the bottom of the table. The first added row, labeled as zj, represents the decrease in the value of the objective function that will result if one of the variables corresponding to the j's column of a matrix is brought into the basis. This middle portion of the table is considered as matrix. The method for determining the value of zj will be discussed later. The second added row, labeled as cj minus zj, represents the net change in the value of the objective function if one of the variables corresponds to the j's column of a matrix is brought into the solution. We refer the cj minus zj row as the net evaluation row. So the modified table looks like this. Columns and rows filled with green color are the newly added ones. The values of the added column are coefficient of the basic variable in the objective function when it's written in standard form as zmax is equal to 400x1 plus 300x2 plus 0s1 plus 0s2. Here the coefficient of s1 and s2 are 0. So the values of the basic variable s1 and s2 is 0. To determine each column value in the zj row, we use the formula zj is equal to summation of cbi plus Aij, where Cbi is the values in the Cb column, that is here, and Aij are elements in the ith row of j column. Thus, the value of Zj corresponding to x1 column is Zj is equal to 0 times 1 plus 0 times 2. 0 times 1 is 0 plus 0 times 2 is 0, which is equal to 0. So we will write 0 here. Similarly, the value of Zj corresponding to x2 column is Zj is equal to 0 times 1 plus 0 times 1. 0 times 1 is 0 plus 0 times 1 is 0, which is equal to 0. Again, we will write 0 here. The values of Zj correspond to S1 column is Zj is equal to 0 times 1 plus 0 times 0, which is equal to 0. 0 will be written here. The values of Zj correspond to S2 column is Zj is equal to 0 times 0 plus 0 times 1, which is equal to 0. So 0 is set here. The values of Zj correspond to Bi column is Zj is equal to 0 times 18 plus 0 times 24. 0 times 18 is 0 plus 0 times 24 is 0, which is equal to 0. We will write 0 at this last column. The values of the net evaluation row is calculated by subtracting Zj from the corresponding Cj. Hence, the net evaluation row corresponding to S1 column is Cj minus Zj is equal to 400 minus 0, which is equal to 400. The net evaluation row corresponding to x2 column is Cj minus Zj is equal to 300 minus 0, which is equal to 300. The net evaluation row corresponding to S1 column is 0 minus 0, which is equal to 0. The net evaluation row corresponding to S2 column is 0 minus 0 again, which is equal to 0. Therefore, the initial simplex tableau looks like this. Boldface 0 at the bottom right hand side is the value of the objective function associated with the current feasible solution. That is, the maximum income when Mr. X doesn't work, any part-time job is 0 per. At this stage, it's important to compare the initial simplex tableau and the standard form of mathematical model in order to draw the relationship between 1. The number of variables in standard form of mathematical model, that's let's say n, and the number of columns in the initial simplex table. And second, the number of constraint equations in the mathematical model, let's say m, and the number of rows in the initial simplex table, because the rows stand for constraint equations and the columns stand for variables. The standard mathematical form looks like this, and the initial simplex table looks like this. It's evident from the comparison that the number of variables are 4, that is x1, x2, s1 and s2, but the number of columns are 7. That means the number of columns greater than the number of variables by 3. Thus, for n number of variables, it's recommended to draw n plus 3 column in setting the initial simplex table. On the other hand, the number of constraint equations are 2, that is, the weekly working hours and the weekly preparation hours. But the number of rows are 6. The number of rows greater than the number of constraint equation by 4. Again here, for m number of constraint equations, it's recommended to draw m plus 4 rows. Step 4. Choose the non-variable variable that will become the new basic variable. This is a step where the initial simplex table will be made ready for first iteration. Iteration is a process of moving from one basic feasible solution to another by selecting a non-basic variable to replace one of the current basic variable while improving the objective function. Criteria for selecting non-basic variable to become a new basic variable. First criteria, look at the net evaluation row, that's Cj minus Zj, and select the variable with the largest value to enter the basis. Why the largest value? Because this is a variable that will cause the largest per unit improvement in the value of the objective function. In case of ties, that's when two or more variables have equal value at the net evaluation row, follow the convention of selecting a variable to enter the basis that corresponds to the leftmost of the column. The column that contains the selected largest value is called pivot column. In our part-time problem, x1 is a non-basic variable that should be selected to enter the basis because its value in the Cj minus Zj row is the largest, and the column containing x1 is a pivot column. Step 5. Determine the variable that leaves the basis by calculating the quotient. When one non-basic variable enters the basis, one of the current basic variable should leave the basis. Criteria for removing a variable from the current basis is by calculating the minimum ratio. For each row, compute the ratio of the value of the basic variable at the right-hand side to the corresponding value at the pivot column for each value at the pivot column greater than 0. The basic variable that will be removed from the basis corresponding to the minimum of these ratios. In case of tie, that's when two or more rows have equal ratio, we follow the convention of selecting the variable that corresponding to the uppermost of the tied rows. To illustrate the computation involved, let's add an extra column to the right of the initial simplex table showing the bi over ai ratio, where bi is the value of the basic variable and ai is the value of the ith row of the pivot column. To evaluate the ratio of bi over ai for the part-time problem, bi over ai corresponding to S1 row is 18 divided by 1, which is equal to 18. bi over ai corresponding to S2 row is equal to 24 divided by 2, which is equal to 12. The minimum ratio is 12. Thus, the variable to be removed from the basis is S2. The row containing the value to be removed from the basis is pivot row. Here, the row containing S2 is a pivot row. The element at the intersection of pivot row and pivot column is called pivot element. In our part-time problem, 2 is a pivot element. Step 6. Calculate the next W. The first and second row of the table remains the same. At column corresponding to basis, S2 is replaced by the new entering basic variable that is x1. 400, which is the coefficient of x1 in the objective function, has to be written at x1 row in the column corresponds to CB. To determine the new elements in the pivot row, divide each value by the pivot element, that is, new value is equal to old value divided by pivot element. New value at pivot row corresponding to S1 column is, old value is 2, divided by pivot element is 2, which is equal to 1. New value at the pivot row corresponding to X2 column is, old value is 1, divided by the pivot element is 2. 1 divided by 2 is equal to 0.5. New value at pivot row corresponding to S1 column is equal to, old value is 0, divided by the pivot element is 2. 0 divided by 2 is equal to 0. New value at the pivot row corresponding to S2 column is equal to, old value is 1, divided by pivot element is 2, which is equal to 1 divided by 2 is equal to 0.5. New value at the pivot row corresponds to bi column is equal to, old element is 24, divided by the pivot element is 2. 24 divided by 2 is equal to 12. New values for rows other than pivot row are calculated by using the formula. New value is equal to old value minus corresponding pivot column value times corresponding pivot row value divided by pivot element. New value of S1 row at column corresponding to S1 is equal to, old value is 1 minus corresponding pivot column value is 1 times corresponding pivot row value is 2 divided by the pivot element is 2. 1 times 2 is 2, divided by 2 is 1, so 1 minus 1 is equal to 0. New value of S1 row at the column corresponding to X2 is equal to, old value is 1 minus new corresponding pivot column value is 1 times corresponding pivot row value is 1. The pivot element is again 2. 1 times 1 is 1, divided by 2, 1 over 2. 1 minus 1 over 2 is 0.5. New value at S1 row corresponding to S1, the column S1 is, old value 1 minus corresponding pivot column value is 1 times corresponding pivot row value is 0 divided by 2. 1 times 0 is 0, 0 divided by 2 is 0, so 1 minus 0 is equal to 1. New value of S1 row at a column corresponding to S2 is equal to old value is 0 minus corresponding pivot column value is 1 times corresponding pivot row value is 1 divided by the pivot elements 2. 1 times 1 is 1 divided by 2, 0.5. 0 minus 0.5 is equal to minus negative 0.5. New value at S1 row at column corresponding to BI is equal to old value is 18 minus corresponding column pivot value is 1 times corresponding pivot row value is 24 divided by the pivot element 2. 1 times 24 is 24, 24 divided by 2 is 12, 18 minus 12 is 6. Calculate the value of Zj row by using the formula Zj is equal to summation of CBI times Aij. Zj corresponding to S1 column is equal to CBI is 0 times 0 plus 400 times 1. 0 times 0 is 0 plus 400 times 1 is 400. 0 plus 400 is equal to 400. Zj corresponding to X2 column is equal to 0 times 0.5 plus 400 times 0.5. 0 times 0.5 is 0 plus 400 times 0.5 is 200. 0 plus 200 is equal to 200. Zj corresponding to S1 column is equal to 0 times 1 plus 400 times 0. 0 times 1 is 0. 400 times 1, 0 is 0. So 0 plus 0 is equal to 0. Zj corresponds to S2 column is equal to 0 times negative 0.5 plus 400 times 0.5. 0 times negative 0.5 is 0 plus 400 times 0.5 is 200. 0 plus 200 is equal to 200. Zj corresponds to Bi column is equal to 0 times 6 plus 400 times 12. 0 times 6 is 0 plus 400 times 12 is 4800. 0 plus 4800 is equal to 4800. Determine the net evaluation row just by deducting Zj from Cj. Cj minus Zj correspond to X1 column is equal to Cj is 400 minus Zj is equal to 400. So 400 minus 400 is equal to 0. Cj minus Zj corresponding to X2 column is equal to Cj is 300 minus Zj is 200. 300 minus 200 is equal to 100. Cj minus Zj corresponding to S1 column is equal to Cj is 0 minus Zj also 0. 0 minus 0 is equal to 0. Cj minus Zj corresponding to S2 column is equal to Cj is 0 minus Zj is 200. 0 minus 200 is equal to negative 200. Interpretation of the result after this first iteration. The bold-faced 4800 at the bottom of the BI column an indication that Mr. X can earn 4800 per week if he works for 12 hours only at job A. Step 7. Test for optimality. If the net evaluation row, that is Cj minus Zj, less than or equal to 0 for all columns, the solution is optimal. That is, no further iteration is needed. If not, return to step 4. In our case, since Cj minus Zj corresponding to X2 is greater than 0, the part-time problem is not optimal. Hence, we need to go to further iteration starting from step 4. Step 4, choose the non-basic variable that will become the new basis. To choose the new basis, just look at the net evaluation row and pick the greatest Cj minus Zj value. In this particular case, 100 is the greatest value in the row. Thus, the variable at the top of the column containing 100 is the non-basic variable that will become the new basis, and the column of X2 becomes the pivot column. Step 5. Determine the variable that leaves the basis by calculating the quotient. To determine which variable will leave the basis, just divide each element under the column Bi to the corresponding element in the pivot column for each value at the pivot column greater than 0. The ratio for S1 row is equal to 6 divided by 0.5, which is equal to 12. The ratio for X1 row is equal to 12 divided by 0.5, which is equal to 24. 12 is less than 24, because S1 is the variable that leaves, and the row containing S1 will become the new pivot row. The element at the intersection of the pivot column and pivot row, that is 0.5 in this case, is a pivot element. Step 6. Calculate the next W. The elements and the variable at the first and second row of the W remains the same. At the third row, the basis S1 is replaced by the new entering basis X2. The coefficient of X2 in the objective function is 300. So CB value of S2 is equal to 300. The remaining values for this row will be calculated later. The next row, X1 and its CB value, Zj and Cj minus Zj remain the same, but their corresponding column values are to be determined. To determine the values of the pivot row, use the formula new value is equal to old value divided by pivot element. Old value is already known, a pivot element is already determined, which is 0.5. New value at the pivot row corresponding to X1 column is equal to the old value is 0 divided by the pivot element is 0.5. 0 divided by 0.5 is equal to 0. Here we will write 0. New value of pivot row as a column corresponds to X2 is equal to old element is 0.5 divided by the pivot element is 0.5. 0.5 divided by 0.5 is equal to 1. Again we will write 1 here. New value of pivot row as a column corresponding to S1 is equal to old value is 1 divided by the pivot element is 0.5. 1 divided by 0.5 is equal to 2. So the value of pivot row at column corresponding to S1 is 2. New value of pivot row as the column corresponding to S2 is equal to old value is negative 0.5 divided by the pivot element is 0.5. Negative 0.5 divided by 0.5 is equal to negative 1. Again, the value of pivot row at the column corresponding to S2 is negative 1. New value of the pivot row at the column corresponding to BI is equal to old value is 6 divided by the pivot element is 0.5. 6 divided by 0.5 is equal to 12. The new value of pivot row at a column corresponding to BI is 12. As usual, the new value for rows other than the pivot row are calculated by using the formula. New value is equal to old value minus corresponding pivot column value times corresponding pivot row value divided by pivot element. New value of X1 row at column corresponding to X1 is equal to old value is 1 minus corresponding pivot column value is 0.5 times corresponding pivot row value is 0 divided by pivot element is 0.5. 0 times 0.5 is 0. 0 divided by 0.5 again 0. So 1 minus 0 is equal to 1. We will write 1 here. New value of X1 row at a column corresponding to X2 is equal to old value is 0.5 minus corresponding pivot column value is 0.5 itself times corresponding pivot row value is 0.5 divided by the pivot element is 0.5. 0.5 times 0.5 divided by 0.5 is 0.5. So 0.5 minus 0.5 is 0. 0 will be written here. New value of X1 row at a column corresponding to S1 is equal to old value is 0 minus corresponding pivot column value is 0.5 times corresponding pivot row value is 1 divided by the pivot element is 0.5. 0.5 times 1 is 0.5. 0.5 divided by 0.5 is 1. So 0 minus 1 is negative 1. So we will write negative 1 here. New value of X1 row at column corresponding to S2 is equal to old value is 0.5 minus corresponding pivot column value is 0.5 times corresponding pivot row value is negative 0.5 divided by the pivot element is 0.5. Negative 0.5 times 0.5 divided by 0.5 is negative 0.5. 0.5 minus negative 0.5 means 0.5 plus 0.5, which is equal to 1. So 1 will be written here. New value of x1 row at a column corresponds to b1 is equal to old value is 12 minus corresponding pivot column value is 0.5 times corresponding pivot row value is 6 divided by 0.5. 0.5 times 6 divided by 0.5 is 6. So 12 minus 6 is 6. Calculate the value of zj row by using the formula zj is equal to summation of cbi times aij. cbi are the values under cb column and aig are the values under corresponding column. zj corresponding to x1 column is equal to 300 times 0 plus 400 times 1. 0 times 300 is 0 plus 400 times 1 is 400. 0 plus 400 is equal to 400. zj corresponding to x2 column is equal to 300 times 1 plus 400 times 0. 300 times 1 is 300 plus 400 times 1 is 0. 300 plus 0 is 300. zj corresponding to s1 column is equal to 300 times 2 plus 400 times negative 1. 300 times 2 is 600 plus 400 times negative 1 is negative 400. 600 plus negative 400 is 200. zj corresponding to s2 column is equal to 300 times negative 1 plus 400 times 1. 300 times negative 1 is negative 300 plus 400 times 1 is 400. Negative 300 plus 400 is equal to 100. zj corresponding to bi column is equal to 300 times 12 plus 400 times 6. 300 times 12 is 3600 plus 400 times 6 is 2400. 3600 plus 2400 is 6000. At last, calculate the net evaluation row, that is Cj minus Zj, by deducting Zj from Cj. Cj minus Zj at column corresponding to x1 is equal to Cj is 400 minus Zj is 400. So 400 minus 400 is 0. Cj minus Zj at column corresponding to x2 is equal to Cj is 300 minus Zj is also 300. So 300 minus 300 is equal to 0. Cj minus Zj at column corresponding to S1 is equal to Cj is 0 minus Zj is 200. So 0 minus 200 is equal to negative 200. Cj minus Zj at column corresponding to S2 is equal to Cj is 0 minus Zj is 100. So 0 minus 100 is negative 100. Interpretation of the result after this second iteration. The bold phase 6000 at the bottom of BI column is an indication that Mr. X can earn a maximum of 6000 birr per week by working 6 hours at job A and 12 hours at job B. Step 7. Test for optimality. To test for optimality, analyze the values as the net evaluation row. If the value of each column are less than or equal to 0, then the solution is optimal. In this case, all the values are less than or equal to 0, thus the solution is optimal, meaning the maximum income Mr. X can earn is 6000 birr per week by working 6 hours at job A and 12 hours at job B. That's all for this session. Next time we will solve fascinating linear programming problem with more than 2 decision variables by using Simplex method. Goodbye.